Equations involving radical expressions. First, let's look at the power rule for solving equations. If each side of an equation is raised to the same positive integer power, then any solutions to the given equation are among the solutions to the new equation. That is, the solutions to the equation a equals b are among the solutions a to the n equals b to the n. Solving a radical equation. Step 1. We'll isolate a radical term on one side of the equation. Step 2. We'll apply the power rule by raising each side of the equation to the power equal to the index of the isolated radical term. Step 3. Solve the equation. If it still contains a radical, repeat steps 1 and 2. Step 4. Check your answers by substituting each result in the given equation. Let's solve this equation symbolically and we'll check our results. The first thing that we want to do is isolate the radical. That's already done for us here. Next, we'll raise each side of the equation to a power equal to the index of the isolated radical. The index is 2, so we're going to raise each side of the equation by a power of 2. When I square the square root of 2t plus 4, I'm left with just 2t plus 4. 4 squared is 16. Now I have a much simpler equation that I can solve. Subtract 4 from both sides. I get 2t equals 12. Divide both sides by 2, and t equals 6. It is essential that we check. So we'll check t equals 6 in the original given equation. So square root of 2 times 6 plus 4 equals 4. That's the square root of 12 plus 4 equals 4. The square root of 16 equals 4, which is true. So we know that for sure t equals 6. On this equation, we will need to isolate the radical. The radical right now is not alone because 3 is being subtracted from it. So what we do to isolate it is to add 3. So we'll have the square root of x plus 3 equals 7. Now we'll raise both sides of the equation to a power equal to the index. So we'll square both sides. That gives me an x plus 1 equals 49. Now I'm going to subtract 1, so x is 48. And we're going to check our solution, x equals 48. Square root of 48 plus 1 minus 3 equals 4. That's the square root of 49 minus 3 equals 4. That means 7 minus 3 is 4, which we know is true. So x does indeed equal 48. Now we need to isolate our radical. First, let's identify what that radical is. The radical part of this equation is simply the square root of x minus 2. That does not include the positive 1 here and the 2 in front of our radical. So we need to isolate this highlighted radical. That gives me, I can subtract 1 from both sides. 2 square root of x minus 2 equals 4. Now to get rid of this 2, I'll divide both sides by 2. That cancels, so I have my radical isolated. And now I can raise both sides of my equation to the index power of 2. That gives me an x minus 2 equals 4 and x equals 6. Now let's go ahead and check. That gives me 2 square root of 6 minus 2 plus 1 equals 5. So 2 square root of 4 plus 1 equals 5. That's 2 times 2 plus 1 is 5, which is 4 plus 1 equals 5, which we know is true. So x equals 6 is our solution. Here I have a cube root. So instead of squaring both sides of the equation, I'm now going to want to cube both sides. So I'm going to cube the left side and the right side. That gives me a 2z minus 4 on the left and a negative 8 on the right. Continuing to solve, I get z equals negative 2. Now I'm going to check that solution of z equals negative 2. That's the cube root of 2 times negative 2 minus 4 equals negative 2. So that's the cube root of negative 4 minus 4 is negative 2. That's the cube root of negative 8 equals negative 2. So negative 2 equals negative 2, and we know that z does indeed equal negative 2. Here we'll need to square both sides of the equation because we have a square root. I square the left side, and for me to square the right side, I'll have to use parentheses. Now when I square the square root, I get b squared minus 4 on the left. On the right, remember I need to square a binomial. If you'll recall, when you square a binomial, you get a trinomial. You'll get b squared minus 2b plus 4, which is b squared minus 4b plus 4. So my right side is the trinomial b squared minus 4b plus 4. Now if I subtract b squared from both sides, that gives me a negative 4 equals negative 4b plus 4. So I don't have a quadratic equation anymore. Now I'm going to subtract 4 from both sides. That gives me a negative 8 equals negative 4b. When I divide both sides by negative 4, it gives me a b equals 2. Of course, we'll need to check. Putting it into the original equation, I have the square root of 2 squared minus 4 equals 2 minus 2. That's the square root of 4 minus 4 equals 0, which I know is the square root of 0. So 0 equals 0 is true, and b does equal 2 for us. The square root of 1 minus 2x equals x plus 7. Again, I'm going to square both sides of the equation. On the left side, I'll have 1 minus 2x. On the right, x squared plus 14x plus 49. Now I have a quadratic equation. I'm going to have to get everything on one side equal to 0. So I'm going to subtract 1 and add 2x to both sides. That gives me an x squared plus 16x plus 48. Now I need to factor this trinomial. Factoring this trinomial, I get an x plus 4 and an x plus 12. So that gives me an x plus 4 equals 0 and x plus 12 equals 0. So x equals negative 4 and x equals negative 12. I'll need to check both of these solutions. So checking x equals -4, I have the square root of 1 minus 2 times -4 equals -4 plus 7. That's the square root of 1 plus 8 equals 3. The square root of 9 is 3, so 3 equals 3. X equals -4 is one of my solutions. Let's try checking x equals -12. I have square root of 1 minus 2 times -12 equals -12 plus 7. This gives me 1 plus 24 is -12 plus 7. So the square root of 25 is -5, and this is not true. So I know that x equals -12 cannot be one of our solutions. In fact, this is what we call an extraneous solution. Whenever we square both sides of an equation in the process of solving, we can often come up with an extraneous solution. This is why checking when we are squaring both sides of an equation is not an optional activity. We do need to check all solutions in the original equation, and then we can throw out any extraneous solutions that may appear at first to be solutions but don't actually check out. So we have just one solution of x equals -4. It's also possible that we could have two solutions, or we could have no solutions on any of these radical equations. Solving the equation x to the nth equals k. Take the nth root of each side of x to the n equals k to obtain the nth root of x to the n equals the nth root of k. If n is odd, then the nth root of x to the nth equals x, and the equation becomes x equals the nth root of k. If n is even and k is greater than 0, then the nth root of x to the nth equals the absolute value of x, and the equation becomes the absolute value of x equals the nth root of k. Of course, if k is less than 0, or in other words, negative, there are no real solutions. Let's solve this equation. We have x squared equals 49, so I know I can take the square root of both sides. Now the question is, considering both of those roots, when I'm solving, I want to make sure that I can find all of the numbers that when I square them, I get 49. So when you are the one putting the square root on a number, you also have the responsibility of putting the plus minus with it. This way we capture all possible solutions. When I take the square root of x squared, I have x. Square root of 49 is 7, so I have a positive 7 and a negative 7 as a solution. And as you can see, 7 squared is 49, and negative 7 squared is also 49. Remember, the old way we would have solved this would be to get everything on one side of the equation, factor, set each factor equal to 0, and then solve those individual equations. So we want to make sure we're getting both solutions. That's the reason we want to capture them all by putting the plus minus. We don't want just the positive answer or the principal square root. We want the positive and the negative square roots of the number when we're taking a square root. Here I'm going to take the square root again. The square root of 3x minus 6 squared equals plus or minus the square root of 25. On the left, this gives me 3x minus 6. On the right, a plus or minus 5. 3x equals 6 plus or minus 5. Now I'm dividing by 3. So this will look funny for a moment, but we'll go ahead and put our 6 plus or minus 5 and divide it all by 3. We don't leave it like that. We can actually figure out the number that this is. So 6 plus 5 is 11, divided by 3 is 11 thirds. Or 6 minus 5 is 1, divided by 3 is 1 third. Now I have a cube, so I'm going to take the cube root of both sides. This gives me the cube root of b cubed equals the cube root of 64. Now when I'm taking an odd root, I don't need to put plus or minus, because remember, it's only even roots where we have a positive or a negative root. For cube roots, we just take the root as it is. So I have here a b on the left. The cube root of 64 is 4. You can show this on the calculator. Remember that your cube root is in the math button. For my calculator, it's option 4. We're taking the cube root of 64 and we get 4. Let's solve the equation symbolically, graphically, which is optional, and numerically. Here I'm going to take the cube of both sides to get rid of my cube root. That gives me 5 minus x equals 8. So negative x equals 3 and x equals negative 3. So now I've solved that symbolically. Let's go ahead and check. When I check this, I have the cube root of 5 minus negative 3 makes 5 plus 3 equals 2. That's the cube root of 8 equals 2. So 2 equals 2. Now let's solve this graphically, and like I said, this is optional. You can always do it by hand. The way we would do this graphically is to first put the left side of this equation into our equation editor. So we have the cube root. Remember, we have to go to the math button to pick up the cube root. The cube root of 5 minus x. And in the second equation, we'll put the right side of our equation, 2. Now when I graph this, you'll see the first equation, that cube root, then you'll see the line. What we want to do is see where those two graphs are intersecting. So I'm going to go into the second calculate menu, and I'm finding the intersection of the first curve, enter, and the second curve, enter, and let's have the calculator give its guess. It says the intersection is negative 3, 2. Of course we know that the y is 2 because we let y equal 2 on that second equation. This is our solution, the x equals negative 3. Now you can solve this by hand just as well as you can solve this graphically. If you wanted to solve this numerically, we would make a table. And we put in here some numbers. And test to see what is going to work. If I put a negative 3 in here, 5 minus negative 3 is 5 plus 3, which is 8. The square root of 8 is 3, so I get a 2. Putting in a negative 2, 5 minus negative 2 is 5 plus 2, which is 7. The cube root of 7 is not going to come out evenly. It's going to be the cube root of 7. And negative 1, we get a 5 plus 1, which is 6. That gives me the cube root of 6. A 0, 5 minus 0 is 5. We get the cube root of 5. A 1, we get 4, cube root of 4. A 2, we get 3, the cube root of 3. And a 3, I get 2, the cube root of 2. And we see in this table the only place that has a 2 is my negative 3. You can't always solve equations numerically, especially when the answers come out to be some kind of irrational number, like maybe 5 square roots of 2. So this is going to be a rarity that we would be able to solve this numerically. Let's solve for the indicated variable. Now that we know how to use powers and nth roots in order to solve equations, we can solve more complicated formulas. Here we have a formula t equals 2 pi square root of L over 32, and we want to solve it for L. So let's go ahead. First off, we probably want to isolate that square root, just like we isolated square roots earlier in this lesson. So how would I isolate that square root? I would want to divide both sides by 2 pi. That gives me a t over 2 pi equals the square root of L over 32. Now that we have the square root isolated, we'll want to square both sides. That gives me a t squared over 4 pi squared on the left, and on the right I'll have an L over 32. Now how would I isolate that L? The L is being divided by 32, so to isolate it I multiply both sides by 32. That gives me an L on the right, and here 4 goes into 32 8 times. That will give me an 8t squared over pi squared. Let's solve this formula for a. Again, I have a square root, so I'm going to want to square both sides of that equation. That gives me an r squared equals a over pi. Now solving for a, I would just multiply both sides by pi. So a equals pi r squared. You might recall the Pythagorean theorem, a squared plus b squared equals c squared. Now a and b are always legs of the right triangle. They're the sides that make the right angle. C is always opposite the right angle. It's always the longest side, and it's called the hypotenuse. Using the Pythagorean theorem, let's find the length of the missing side in the right triangle. Here I have a B. This must be side A, and this must be side C. So I have a squared plus b squared equals c squared is 24 squared plus b squared equals 25 squared. Now I have a 24 squared. If you'd like, we can put this in the calculator. Let's go back to the home screen. 24 squared equals 576 plus b squared equals 25 squared, which is 625. Now I want to isolate my b squared, so I'm going to subtract 576 from 625. I get 49. Now, solving this, I would take the square root of both sides. So that's the square root of b squared and the square root of 49. And of course, we have to put the plus minus in there. So b is plus or minus 7. Now, in the context of this problem, where we're talking about b being a length of a leg, the answer -7 doesn't make sense. So we throw the -7 out, and b equals 7 is our only solution. A right triangle has legs A and B with hypotenuse C. Find the length of the missing side. So here, we don't have a picture, but we can go ahead and draw one on our own. Here's our right angle, and we have legs A and B. Remember, the legs are the sides that make up the right angle. And we have to find the hypotenuse, which we know is C. So a squared plus b squared equals c squared gives me 3 squared plus 4 squared equals c squared. That's 9 plus 16 equals c squared. So 25 is c squared. I'll take the square root of both sides, remembering the plus minus, and c equals plus or minus 5. Again, in the context of this problem, it doesn't make sense to have a negative length. So I'm going to throw out the -5 and keep just a +5 for my solution. Now we have the distance formula. The distance d between the points x1, y1 and x2, y2 in the xy plane is this formula. D equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. This comes directly from the Pythagorean theorem. If we would have these 2 points in the plane, let's call this point x2, y2, and this point x1, y1. Then we can find the distance between those points by using the Pythagorean theorem. Dropping a perpendicular and moving out horizontally to make that right angle. Now the length of this side is going to be x2 minus x1. The length of this side is going to be y2 minus y1. So now we need to find out the length of this side. We'll call it d, which is the distance between those 2 points. So using the Pythagorean theorem, where this is a and this is b, I would have x2 minus x1 squared plus y2 minus y1 squared, and that equals my d squared, my hypotenuse. Now to get the d by itself, I simply take the square root of both sides. And I know I'm not going to put the minus because this is talking about a length or a distance which can't be negative. So that gives me my distance formula, which came directly from my Pythagorean theorem. Let's find the length of the line segment. Here I could just go ahead and draw a right triangle and use Pythagorean theorem, but let's go ahead and practice our formula for distance. Remember, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. So I have here the square root of, well, let's find our points here. Our points here are -2, 1, and 2, 3. So this gives me the x of the second point, which is 2, minus the x of the first point, which is a -2, so it makes it a +2 quantity squared, plus y2, which is 3, minus y1, which is 1, all squared. So d is the square root of 2 plus 2, which is 4, squared, plus 3 minus 1, which is 2, squared, is 4. So d is the square root of 20, which I know I'm going to have to simplify. Remember that 20 is 2 times 10, 10 is 2 times 5. So I'll have the square root of 2 squared times the square root of 5, which gives me 2 square roots of 5 for the exact length of that line segment. Let's find the distance between these points. Now here I'm not going to have a graph. I'm not worried about graphing it. Let's just use the distance formula. So the distance is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So d is going to be the square root of 4 minus -1, so it makes it 4 plus 1 quantity squared, plus y2 minus y1, so that's 10 minus 2 quantity squared. So I have the square root of this is 5 squared, plus 10 minus 2 is 8 squared. So the distance is going to equal 25 plus 64 in my square root, which is the square root of 89. Now 89 is not going to break down, so that's just our distance, the square root of 89. The diagonal of a television. A rectangular television screen is 11.4 inches by 15.2 inches. Find the diagonal of the television screen. So here we can draw a picture. It's 11.4 inches by 15.2. And they want to know what the diagonal of that television screen is. So again, we're using the Pythagorean theorem. This is A, this is B, and we're finding C. So 11.4 squared plus 15.2 squared equals my C squared. Let's use our calculator. We have 11.4 squared is 129.96, and 15.2 squared is 231.04, and I'm going to add those together. And that gives me 361. And we need to take the square root of that, so second square root, and we can hit second answer right there, and it's going to take the square root of the answer from my last line, the 361, and I get 19. So we have here 19 inches as our answer. So that covers this lesson. Go ahead and try your homework and be sure to let me know if you have questions.